So first of all, we have a 100 times 1 minus alpha percent confidence interval. You should not stop there. You should say what it's for. There are different formulas for confidence intervals in different situations. Say what you're trying to estimate. To estimate a population mean, mu, the book phrases this on mu, but that's sort of weird phrasing in my mind. What does on mu mean? It means to estimate mu when the population variance is known, meaning also the population standard deviation is known. Very, very unrealistic, right? If you don't know mu, why would you know sigma squared? It's almost silly. We do it for the purpose of keeping things simple at first. Some people, you might say, do it all the time because they're always trying to keep things simpler, but in that case, it becomes less accurate. Both theory and simulation can demonstrate that it's less accurate. For our purposes, it's used because it's just, at first, because it's just simpler. X bar plus or minus, I'm going to write something I did not write last time first here, plus or minus E. X bar is your point estimator. When we were talking about things like X bar, capital X bar, and S, capital S squared and capital S, those are statistics that are also called point estimators. Why did we call them point estimators? Because we're using them to estimate one number. An observed value of X bar, observed value of capital X bar would be labeled little x bar. It would be a point estimate. When the theoretical thing that's a random variable is called an estimator, or estimator if you want to say it fast. I tried to make a point of saying it slow and say estimator. Whatever its observed value is a point estimate. E is the margin of error I will tell you that some books don't call it E, some books call it M for margin. But I'm aware that Dr. Wetzel likes to call it E for error. I did make it a capital E here, though. I did make it a capital E, though in this circumstance, it's actually not a random variable. When we know sigma squared, and if the sample size is fixed, here is the formula for that margin of error. And that expression, z sub alpha over 2 times sigma over square root of n, again, if sigma is known and n is fixed and alpha is given, that's not a random variable. Okay, I'll go ahead and use a capital E anyway. In the case where sigma squared is unknown, the realistic case, which I'll write down in a minute, and I have to use a capital S there instead of a sigma, then it does become a random variable. So in that more realistic case, not only is the point estimator a random variable, but the margin of error itself is a random variable. In this case, it's not really a random variable, but I'll use a capital E anyway. There's the formula where z sub alpha over 2 is a critical value for the standard normal distribution. So this is supposed to be a picture of normal curve with mean 0 and variance 1, also meaning the standard deviation is 1. Inflection points would be at plus or minus 1. And z sub alpha over 2 is some point, say right there, where the area under the curve to the right of this point of this critical value is alpha over 2 in probability notation, i.e. the probability that capital Z is greater than or equal to z sub alpha over 2 is alpha over 2. That is equivalent to saying the probability that capital Z is less than or equal to negative z sub alpha over 2 is also alpha over 2. Negative z sub alpha over 2 would be over here. Notationally, you could also write that as z sub 1 minus alpha over 2. And by symmetry, these things, that's also by symmetry. This, more by symmetry, this is equivalent to saying the probability that capital Z is between negative z sub alpha over 2 and positive z sub alpha over 2. That probability is 1 minus alpha for this 100 times 1 minus alpha % confidence interval. This picture and these kinds of probabilities, you should work at these being in your head and very naturally without having to think about it very much. And again, the most typical value for alpha to use is 0.05. And if alpha is 0.05, that corresponds to 100 times 1 minus alpha % being 95%. It corresponds to alpha over 2 being 0.025 and z sub alpha over 2 being 1.96 as your best two-place decimal approximation. And again, I said this last time, and I don't think it's wrong. That number, 1.96, is the one number that shows up the most in statistics. Because people seem to always be doing 95% confidence intervals, and when they're using a z distribution, they use 1.96. If alpha is something different, then you get a different answer there. You can find this with the table. You should practice finding this with the table in the back of the book. That's worthwhile to do. Make sure you can figure out how to use the table. You'd want to look for, it's the CDF for a standard normal. In the table, you'd want to look for an area equal to 0.975 to find this. Why 0.975? Because if the area between negative z sub alpha over 2 and positive z sub alpha over 2 is 0.95, then the area to the right, left of z sub alpha over 2 would be 0.975. So to find it in the table, you'd have to look for 0.975. That is worth you doing after class today. Okay, I think you can remember to do it. Double check that. Make sure you double check it with your technology too. You can use InvNorm or normal CDF with some experimentation. I think I did it last time even. Try it again. Okay, and as far as using the interval, you just use the formula. You got some data, you got data from a random sample, observe values of X bar. You got to calculate little X bar. If you're using 95% confidence, you use 1.96 right there. You have to be given what sigma is. Oh, got to do it again. Never, ever, 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 ever use sigma from your calculator. Don't ever be tempted to use it. Don't do it in this class. If you do it on the job, it's not my fault if you get fired. Would you get fired? Probably not, but yeah, the calculator does it because some people like to buck tradition and like to use sigma instead of S. I'm not one of those people. Okay. So for me in this class, don't ever use sigma. In order to use this formula, you have to be given sigma or given sigma squared and take its square root. Maybe in the problem statement, it doesn't say sigma equals this or sigma squared equals this. Maybe it just uses words. The variance is 17.3. That would mean sigma squared is 17.3. They might put the word population in there for emphasis. The population variance is 17.3. Take its square root to find sigma. Take the square root of the sample size to get this. You should feel comfortable writing the answer in plus or minus notation or converting to interval notation. Find the left endpoint and the right endpoint, right? The business stats students have trouble going back and forth between those two things. You should not, right? You're probability and statistics students, right? Math, computer science, engineering majors. Okay, you should have no trouble going back and forth. And also, here's another big thing if you ever teach stats. Maybe this is you, and if it's you, I'm not saying that's the worst thing in the world, but people get inequalities mixed up, like the direction that they should go. And you'll find this, and they with interval notation, right? It should be the smaller number on the left and the bigger number on the right. They switch it around. Oh, no. Right? Future teachers. Okay, it's happening to me with my statistical analysis students, business stats. Some of them are even like 25 years old or something. They're still getting inequalities mixed up. You know, if your interval is, let me use a different letter like Y or something, 2 is less than Y, always put the bigger number on the right, right? And if you're using interval notation, it's this, it's not 5-2. So in 3rd grade, the teacher for my daughter's class said, it's like it's a little Pac-Man, and Pac-Man wants to eat the bigger number, right? This little, it's like a little mouth. It wants to eat the bigger number. That's the way they remembered it. They also have trouble recognizing that this kind of statement is equivalent to this kind of statement, right? Now, these mean the same thing. All right. We usually write it this way, and that's better in terms of thinking about a number line. I mean, it's understandable why people get confused. You know, sometimes I get confused, like which hand's my left hand? No, okay, right and left hand is fine. Use my right because I'm right-handed. I don't know if you experience this. When you're driving around, like, I don't know if you experience this, north and south, it's sort of easier to figure out which direction is north and which one's south. East and west, I always have to stop and think about it. Oh yeah, if I want to go to Wisconsin, that's east. If I want to head toward North Dakota, that's west. Okay. You have to stop and think a few more seconds about east and west. I experienced that. So don't feel bad if you do. But yeah. You have more trouble with north and south?
No, I have trouble with all the directions.
Oh, all the directions. Okay. I don't know. North and south feels easy. North is like go that way to get even colder, right? And south is go that direction to get warm. I don't know. It feels easier to know which direction is north and south to me. 100 times 1 minus alpha % confidence interval to, okay, I'll say on mu, but really to estimate mu when sigma squared is unknown. All right. In reality, you should almost always use this. Unless you're in a situation where it's just a textbook problem. Or you just forget how to do it this way. And so you're like, okay, I'm going to use the other one. Capital X bar plus or minus capital E. And now capital E itself is also a random variable. Capital X bar plus or minus T sub alpha over 2 times capital S over square root of n. That is a capital S there. With T coming is a critical value of a T distribution, but which T distribution? We barely introduced T distributions for a few minutes at the end of class on Tuesday. Let's get into a bit more depth about T distributions. I'll just say initially here, this is based on a t distribution. Based on a t distribution, also called student's t distribution. Why? Because if you read about this, there's that Gossett person who's not related to Nathan Gossett or his dad, Eric Gossett. From about 100 years ago, he's trying to keep his identity secret. So he called himself student. And so it stuck. Student t distribution with a certain number of degrees of freedom, n minus 1 degrees of freedom, in fact. What does degrees of freedom really mean? I don't really want to go into details. You just kind of accept it. I mean, you can do some research and try to figure out why it's called degrees of freedom. We also said S was computed and S squared were computed using n minus 1 degrees of freedom. I hinted at the reason for that was that in the formula for S squared, we effectively replaced mu with x bar. I don't know if you remember that. If you can visualize what the formula looks like in your head. Don't worry about it. That's just what it's called. What is a t distribution? It does look similar to a normal curve. In fact, similar to a standard normal curve. It is centered at 0. But the standard deviation is not 1. It's bigger than 1. And it depends on the number of degrees of freedom. So this is t distribution with, say, n minus 1 degrees of freedom. Shorthand for that would be t sub n minus 1 is the shorthand. What is the degrees of freedom? I mean, you could try to figure it out from the PDF. I will tell you the PDF in the book has a typo in it. Yeah, I did mention at the beginning of the course, our book has a lot of typos. I haven't spent the time trying to catalog them all. But if you run across various things that look like typos and you're like, is that a typo? It very well may have been. The PDF for the t distribution with little gamma degrees of freedom is there, except there's a typo. The numerator of that fraction should not be capital gamma of little gamma plus 1 all over 2. It should be capital gamma of little gamma plus 1 over 2. The over 2 is inside the parentheses, inside the function.
What page is that on?
It's page 264. So that's not quite the formula for the PDF. So if you were after trying to figure out the standard deviation, what would you have to do? You'd have to find the mean first. You'd have to integrate t times this from minus infinity to infinity. Could that be done by hand? Yeah, I think it probably could be done by hand. You could do a substitution. Let u equal this thing, 1 plus t squared over gamma, and then du would be 2t over little gamma dt, and I think it would work. Actually, you wouldn't even need to do that. The mean's obviously 0 because it's symmetric about 0. Second moment, integrate t squared times that. That sounds harder. Find the variance with the computational formula, take its square root to find the standard deviation. Let's just ask Mathematica what it is. Mathematica, what's standard deviation of student t distribution? Mathematica does student t distribution with gamma degrees of freedom. If little gamma is greater than 2, it's that. Evidently, if little gamma is 2 or 1, maybe the standard deviation does not exist. Yeah, if you plot this thing as a function of little gamma, starting near 2 and going upward, looks like that. there's what the graph of the, what is this? This is the standard deviation of the student t-distribution with little gamma degrees of freedom looks like as a function of little gamma, if you assume little gamma is continuous, which it's really not. Little gamma for student t-distribution is discrete, 1 or 2 or 3 or 4 or 5, etc. But you can certainly graph this as a function of a continuous variable. You see it look like this. You see it does seem to have a horizontal asymptote at 1. So as little gamma gets larger and larger, the student t-distribution gets to be tighter and tighter. The standard deviation shrinks. It's getting skinnier and taller. It's getting to look more and more like a normal distribution, in fact. We can make a plot of PDF student t-distribution. Gamma x, compare it with the PDF of a standard normal distribution. Mean 0, standard deviation 1 of x. X going from -5 to 5, and I put a gamma in there, so I need to animate this with manipulate, say. Let gamma get bigger and bigger. I don't know if Mathematica can graph a student t-distribution for non-integer values of gamma. Maybe it can. So which one's the student t? It's got to be the blue one. That's the one that's a bit more spread out and lower. But as gamma increases here, the blue one approaches the gold one, which is a normal. Gamma is large enough, they're practically indistinguishable. So yeah, as gamma gets larger and larger, the t-distribution approaches a normal distribution. But especially for small values of n, you want to use a student t-distribution with n-1 degrees of freedom. Both of these formulas, to be truly accurate in terms of the confidence level, have to be based on the population being normal. Ugh. Oh, but wait a minute. By the central limit theorem, if n is large enough, x bar is approximately normal anyway, and also by robustness, people go ahead and use the formula anyway if n is large enough. How large is large? Most people try to get away with using this formula if n is at least 25. But certainly, if n is less than 25 and you can tell your population is not normal, you really shouldn't use the formula if you want accuracy. You can look for more detail on these kinds of ideas online, Wikipedia. Look up robustness or something like that. Robustness of a t confidence interval to estimate a mean. And don't forget about what these things mean. Another use of the word mean. Okay, here I go again. Don't ever think. Don't ever think that when you compute one of these intervals, that for sure mu is in there. Don't ever think that. What else? I was going to say something else, but now I'm forgetting what the other don't ever think is. Don't ever think that it contains like 90, if it's a 95% interval, don't ever think it contains 95% of the data. No, it doesn't. So what does the 95% mean if it's a 95% interval? It could be thought of as a probability before the fact. Before you compute the interval, I'm about to compute a 95% confidence interval, either this way if I know sigma squared or this way if I don't. Probability is before the fact. There's a 95% probability that the answer I get will contain mu. But after the fact, technically it's no longer a probability. There's no more randomness involved. You got an answer, either mu's in there or not. Now, again, you might say that's a distinction without a difference. If somebody truly knows mu and they're betting you whether it's in there or not, you're going to bet money. You probably should bet money that it is in there. If you've done everything right. There's no funny business going on. But technically speaking, it's no longer a probability. So we call it a confidence level as a compromise. I'm 95% confident that mu is in there. I'm very confident. High probability of being in there. Don't say that. Just say I'm highly confident. I'm 95% confident. How could you be 99% confident instead of 95% confident? Get a bigger interval. Use a bigger value of Z or T. Let's take an example. You know, maybe you got data. I'm not going to take the time to do a data example, but you have homework problems with data. You got to plug the numbers in your calculator or a spreadsheet. You got to compute X bar. Let's say you also compute S. The calculator will show you S, right? When you do the one variable stats. On a spreadsheet, if you do equals STDEV, spreadsheets are programmed in that case to compute sample standard deviations, dividing by n-1. If you put a p on there, then it would divide by n. Don't ever do that. Don't put a p on there. This will compute S, not sigma. And then you put your cell range, say S1 through S25 here or something like that. Get an observed value of S. By the way, that updated everything, and including my histogram. And that one looks a bit more normal for that particular run. Everything got updated. In Mathematica, does standard deviation do sample standard deviation divide by n-1? I think it does, though I haven't looked it up recently. Say you get 2.34 here and 1.76 there, and n is 25. And alpha, let's do 0.05. N being 25 means the degrees of freedom, which some books write df and some books write little gamma, would be n-1, it would be 24. So I'd be after t sub 0.025. Rewrite that. T sub 0.025 with the degrees of freedom being 24. Can your calculator do that? Yep. Go to the distribution menu, look for inv t. Inv t. The 0.025 is an area to the right, so we want an area to the left of 0.975. DF is 24. What should this number be? It should be bigger than 1.96. For the given level of confidence, 95%, the t value should be bigger than the z value. 2.064. 2.064. What about the table in the back of the book for the t distribution? Here it is. Page 699. T distribution. There's the gamma. This is the degree of freedom column. We're looking for 24 degrees of freedom right there. These numbers are areas to the left. You can see the shading are areas to the left. Our subscript was 0.025, so we're looking for 0.975 right there. Go down to 24 degrees of freedom. 2.03, oh no, 2.064. Yeah, 2.064. And that's what you would plug in. Plug all these numbers into this formula. I won't take the time to do that. They are observed values. You use lowercase letters for X bar and S. This is supposed to be a lowercase s. Yes, but even this is based on the assumption of a normal distribution for the population. But it's robust, as long as n is large enough and the population is not too far from normality, it still is used, is pretty good. Are these the only possible formulas for such confidence intervals? No, they're actually not. There are infinitely many different kinds of confidence intervals you could write down with the same level of confidence. But these are the simplest. They're centered on X bar for one thing. And do keep in mind, different samples will give you different answers. There's no unique answer for a confidence interval to estimate a mean in a given situation, because it depends on what your sample data turn out to be. Different samples will produce different values of X bar and different values of capital E in this situation, different values of S. You'll get a different interval. Here's another way to interpret the 95% of the time, 95% confidence level. If you do that over and over again, hundreds and hundreds of times, maybe thousands and thousands of times, about 95% of the intervals will contain mu. I could take the time to do that in a spreadsheet. Sounds too time consuming. We need to move on.